Topic is tree. A tree is made of nodes, where each node contains a left reference, a right reference, and a data element. The topmost node in the tree is called the root. Every node in a tree is connected by a directed edge from exactly one other node. This node is called a parent. On the other hand, each node can be connected to arbitrary number of nodes called children. Nodes with no children are called leaves or external nodes. Nodes which are not leaves are called internal nodes. Nodes with the same parent are called siblings. So, how to define tree? Tree is a non-linear data structure that is collection of nodes and represents hierarchical relationship between individual data atom. In tree data structure, every individual element is called as node. Node in a tree data structure store the actual data of that particular element and link to next element in hierarchical structure. See, figure shows structure of a tree. In the figure, A, B, C up to K are nodes and connect two nodes with draw line. Line indicates edges. Here, tree with 11 nodes and 10 edges. In any tree with n nodes, there will be maximum of n minus 1 edges. Next, representation of tree. A tree data structure can be represented in two ways. First, list representation. Second, left child, right child sibling representation. Now consider a tree. Now this figure shows a tree. Now first we discuss list representation. In this representation, we use two types of node, one for presenting the node with data and another for presenting only references. We start with a node with data from root node in the tree. Then it is linked to an internal node through a reference node and is linked to any other node directly. This process repeats for all the nodes in the tree. Now this figure shows representation of a list. Next, left child right sibling representation. In this representation, we use list with one type of node which consists of three fields, namely data field, left child reference field, and right sibling reference field. Data field stores the actual value of a node. Left reference field store the address of the child field, and right reference field store the address of the right sibling node. See the first figure. In this representation, every node data field stores the actual value of that node. If that node has a left child, then left references field stores the address of that left child node. Otherwise, that field stores null. If that node has a right sibling, then right reference field stores the address of right sibling node. Otherwise, that field stores null. Now see this figure, pictorial representation of the left child right sibling node. Next is basic terminology of tree. In a tree data structure, use the following terminology. First, root. In a tree, the first node is called as root node. Every tree must have a root node. There must be only one root node. Here, A is the root node. Second terminology is edge. In a tree, the connecting link between any two nodes is called as edge. There will be a maximum of n minus 1 number of edges. See the figure. Here, connect two or more nodes to draw line. Line indicates edges. Next, parent. In a tree, the node which has a child oblique children is called as parent node. It is also be defined as node which is predecessor of any other node is called as parent node. See the figure. Here A, B, C, E and G are parent nodes. Next is child. In a tree, the node which has link from its parent node is called as child node. It can also be defined as the node which is descendant of any node is called as child node. In a tree, any parent node can have any number of child nodes. All the nodes except root are called child nodes. See the figure. Here, B and C are children of A, G and H are children of C, and K is child of G. Next is sibling. In a tree, the nodes which belong to same parent are called as siblings. In can also be defined as the nodes with the same parents are called as sibling nodes. See the figure. Here, B and C are siblings, D, E and F are siblings, G and H are siblings, and I and J are siblings. Next is leaf. In a tree, the node which does not have children is called leaf node. It can also be defined as leaf is a node with no child. The leaf nodes are also called as external nodes. Leaf node is also called terminal node. External nodes oblique terminal nodes are also a node with no child. See the figure. Here D, I, J, F, K and H are leaf nodes. Next, internal nodes. In a tree, the node which has at least one child is called as internal node. It can also be defined as every non-leaf nodes is called as internal nodes. Internal nodes are also called as non-terminal nodes. See the figure. Here, A, B, C, E and G are internal nodes. Degree. In a tree, the total number of children of a node is called as degree of that node. It can also be defined as the degree of a node is a total number of children it has. See the figure. Here, degree of B is 3, degree of A is 2, and degree of F is 0. Next, level. In a tree, each step from top to bottom is called as level and the level count starts with 0 and incremented by 1 at each level stepwise. See the figure. Level 0, then level 1 and then level 2 and then level 3. In this figure, there are the total 4 levels start from 0. Next is height. In a tree, the total number of edges from leaf node to a particular node in the longest path is called as height of that node. In a tree, height of tree is the height of the root node. See the figure. Here, height of all leaf nodes is 0 and height of tree is 3. Next is depth. In a tree, the total number of edges from root node to a particular node is called as depth of that node. In a tree, the total number of edges from root node to a leaf in the longest path is called as depth of tree. See the figure. Here, depth of root node is 0 and depth of tree is 3. Next is path. In a tree, the sequence of nodes and edges from one node to another node is called as path between those two nodes. Length of a path is total number of nodes in that path. See the figure. Here, path between A and J is A implies B implies E implies J has a length 4 and path between C and K is C implies G implies k has a length 3. Next, subtree. In a tree, each child from a node from a subtree recursively. Every child node will form a subtree on its parent node. See the figure. Now next topic is binary tree. Binary tree is a special type of tree in which every node can have a maximum of two children. One is known as left child and the other is known as right child. In a binary tree, every node can have either 0 children or 1 child or 2 child, but not more than 2 children. See the figure shows a binary tree. Next, types of binary tree. There are three types of binary tree: strictly binary tree, complete binary tree, and extended binary tree. First type is strictly binary tree. A binary tree in which every node has either 2 or 0 number of children or none is called strictly binary tree. Strictly binary tree also called as full binary tree or proper binary tree or two tree. Now see the figure. Second type is complete binary tree. A binary tree in which every internal node has exactly two children and all leaf nodes are at same level is called complete binary tree. Complete binary tree is also called as perfect binary tree. Now see the figure shows a complete binary tree. In a complete binary tree, all the nodes must have exactly two children and at every level of complete binary tree there must be two level number of nodes. For example, at level 2 there must be 2 to the power 2 equal to 4 nodes, and at level 3 there must be 2 to the power 3 equal to 8 nodes. A next type of binary tree is extended binary tree. A binary tree can be converted into full binary tree obtained by adding dummy nodes to existing binary tree is called as extended binary tree. Now see the figure shows a extended binary tree. Now next topic is representation of binary tree in memory. There are two ways for representing binary tree in memory. First, array oblique sequential representation. Second, linked list representation. Now first, array representation. In array representation of binary tree, we use a one-dimensional array to represent a binary tree. Now consider a binary tree. In the above binary tree is represented in 1D array. Now, to represent a binary tree of depth n using array representation, we need one dimensional array with a maximum size of 2 to the power n minus 1, 2 to the power n plus 1 minus 1. Next is linked list representation. In a linked list representation of binary tree, we use double linked list to represent a binary tree. In a double linked list, every node consists of three fields. First field for storing left and address, second for storing actual data, and third for storing right child address. In this linked list representation, a node has a following structure. See the figure first. Now this below figure shows binary tree represented using a linked list. See the second figure. Next, operation on binary tree. Now first operation, evaluate the arithmetic expression represented by a binary tree. Second, traversing a binary tree. Third operation, determine the height of binary tree. Fourth operation, determine the weight of binary tree. Fifth operation, determine the total number of nodes in binary tree. Sixth operation, determine the total number of leaves in binary tree. Seventh operation, display the binary tree. Eighth operation, obtain the infix form of an expression. Ninth operation, obtain the prefix form of an expression. And 10th operation is obtain the postfix form of an expression. Now these are the operations on binary tree.